Historically, city design was a top-down process, a single architect at a drafting table sketching a rigid grid for a specific site. But as global populations surge, that traditional method is struggling to keep pace. Traditional static engineering has hit a wall. In high-density environments, packing more people into the same footprint often leads to stagnant air and rising temperatures. To solve this, you have to balance structural loads, local wind speeds, heat island effects, and public space all at once. For a human designer, manually calculating these millions of conflicting variables is impossible. Blueprints are static documents. They cannot navigate this level of complexity. The modern city has become too intricate for linear human calculation. The response to this complexity is embodied intelligence. We are moving artificial intelligence into the physical world, giving it the tools to interact with and shape our environment in real time. Instead of just analyzing data, these systems autonomously iterate physical forms. To do this, they rely on the same logic that drives biological survival, natural selection. The engine runs on a generate and test cycle using 3 core operators: recombination, mutation, and selection. The algorithm blends successful designs, introduces random variations, and discards any versions that fail to meet performance goals. This shifts the focus from drawing buildings to evolving them. We define the environmental constraints, and the algorithm breeds thousands of generations until it identifies the most efficient solution. The optimization process starts with a baseline urban block in its raw wireframe state. During the generate and test cycle, the algorithm explores thousands of spatial configurations in seconds. These pink highlights show the machine testing different ways to distribute mass to maximize density and open space. The final result is a geometry that resembles biological networked venation. Notice the emergence of green and red zones. These are elevated public walkways and terraces that were evolved, not drafted. This specific configuration maximizes the area for residents to gather while using the upper building layers to shade the streets, lowering the temperature at ground level. The algorithm identifies high-density geometries that provide structural integrity and open space in a configuration that human intuition cannot replicate. These building forms are then tested in a 3D voxel grid, a digital environment simulating how the city interacts with the atmosphere at a macro scale. The system analyzes frontal area density to identify where wind will hit a building face. It then carves ventilation paths through the urban core, creating corridors that flush out heat and prevent the air from stagnating. These airflow maps are vital for the next layer of city infrastructure: automated logistics. In a dense city, unmanned aerial vehicles must navigate obstacle-rich environments and dangerous wind-induced wake vortices. By utilizing specialized algorithms like whale optimization, these drones can be routed through the stable wind corridors the city was designed to produce. These paths are 13% more efficient than standard flight routes. By optimizing building geometry for airflow, the system establishes the physical conditions required for these automated logistics networks to operate safely. When we aggregate these optimizations and real-time wind data across thousands of blocks, we create an urban digital twin. This city-wide simulation utilizes a constant feed of environmental variables, allowing planners to use adaptive design, preemptively testing how future expansions impact airflow and energy efficiency. Modern infrastructure is built to update. It functions as a performance model that tracks and reacts to its environment as conditions shift. This shift changes the very purpose of the human architect. If the machine handles the iterations and the physics, what is left for the designer? The architect has become a curator. The focus has moved from drawing specific shapes to managing the rules and parameters that generate them. Human intent now exists at a higher level. We set the performance goals and the fitness rules that guide the algorithm's evolution toward a sustainable result. By embracing this artificial evolution, we have the new tools to build high-performance cities that adapt and breathe like living organisms.